So before we go any further, it's now time to talk about security a little bit. Now, we just identified one of the concerns, which is that storing passwords in plain text is not a good idea. I have to stress this again. You should never, ever, 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 under any circumstances, save a user's password in your database using plain text. But you might ask me, so then how are we supposed to store them? Well, the answer is that we hash those passwords first. And before we explain what that is, let's start with the why. Now, for those of you who are unfamiliar with hashing, I bet some of you are saying in particular, like, you say we shouldn't store passwords in plain text, but you haven't given me a reason. What's the big deal? Well, let's say we do decide to keep the passwords just as they are in plain text like this. We head into pSQL and we say, cool, connect to wedding registration DB. And we select all from users, and we see the password. Okay, maybe it's a little freaky, but not a big deal, right? Well, anyone who works on an application would be able to see each user's password whenever they want. And so if one of them decided to do nefarious things, you could be held liable. It's a bad call. It's just not a good idea. But even if we could completely trust everyone who ever has access to our database intentionally, we can't trust the rest of the internet. In particular, if our application were to be hacked, every user's password would be available to the hacker without any additional effort. And given that most people reuse passwords for multiple applications, that situation could become a security nightmare. Instead, what we're going to do is generate a unique hash for each user's password upon registration, and then instead of storing this plain text password, we're going to store the hashed password in the database. So then when the user attempts to log in, we simply hash the submitted password using the same algorithm and then check the output against what we have stored in the database for that user. Using this approach obfuscates the user's original actual password and still gives us a way to securely authenticate users. Let's write a small script that at least explains a little bit about what we're talking about here. So I'm going to exit pSQL and I'm going to touch a security.js file. And inside the security.js file, I'm going to write a tiny bit of code, and we're going to require Bcrypt, which is one of the packages we installed at the very beginning when we started building this application. And then I'm going to define a password, which is just going to be the same thing, super secret password. And then I'm going to use, okay, thank you, Mac, Bcrypt to hash that password, and I'm going to get a callback here with the hashed password and a potential error, and we're just going to console.log password is PW, and then I'm going to console.log, I always spell password wrong, we'll say hashed password is, and we'll get the hashed password. Now, ignore the 6 that I put here for now. We're going to talk about it in just a quick second. So go ahead and save that, and then run that file so we can see the output, and then we're going to chat about it. So we'll say node security.js, and boom. Ooh, interesting. We see the plain text password, and then the result of running bcrypt.hash on that password. Now, it returns this long, complex, cool-looking thing here. It's just a string, again, nothing super crazy, but this is the result of running the hashing algorithm, a one-way function, on the original plain text password here. Now, it's pretty cool, and the reason we do this, and the reason why we use a hashing algorithm, is because one-way functions are irreversible. So nefarious actors can't take this hashed password and then somehow work backwards to get the plain text password. At least they can't do it through that method alone. However, that doesn't mean it's impossible. Hackers can create what are known as rainbow tables, which is a system where an attacker can build like a list of hashes of every possible password with every possible combination and store this list in some massive data storage system. And then all they need to do is look up this hashed password in their rainbow table, and they'll get the original password with very little computational cost. Now, this is a problem, but to combat this problem, Bcrypt does something kind of cool. It adds this unique salt to the hashing algorithm each time it hashes a password. And the salt is just an additional random string that is added somewhere in the password, so that if user A and user B have the same password, the output is a different hash. And that is the reason that running the algorithm the same password multiple times returns different results. So let's check that out. Let's see it happen. I'm going to run this again. It should be on the same password. And we see that I can run it a bunch of times in a row, and it gives me a different password each time. Kind of cool, right? Now, there's another couple things I want you to notice here. The first is that every single one of these passwords starts with this $2B $. $2B $. And the 2B is what's known as the ident, and it just specifies the version of the Bcrypt algorithm that's used when creating the new hash. Now, if you look directly after that, at that next $sign is $06 $. So it looks like this, and every single one of these passwords starts with that. Now, this is another interesting. This is what's known as the Bcrypt work factor, and just identifies how many rounds are used to hash the password. And technically, it's log rounds, so it's actually 2 to the 6th power. But what this means is that when Bcrypt does the encryption, it takes the salt, it adds it to the plaintext passwords, it uses that whole string to encrypt itself multiple times, again and again and again and again and again. And it does this for a pretty long time. And this slows down the entire process of hashing the password, which is, you might think is a bad thing, but is actually a good thing. Now, the 6, you might wonder, where does the 6, this Bcrypt work factor come from? We defined it right here. Cool enough. And this, using the 6 and the salt, allows us to get this huge string right here. And in fact, you might be asking, like, hey, where is this salt thing you speak of? Well, the salt is actually, I think it's just this part right here. If I were to look correctly. This first part is the salt that is used in the encryption algorithm, and then this is the output of encrypting the plaintext password again and again and again with this unique salt. And you can see that each of these has a different salt here. I think this one's like 21 characters, if with a work factor of 6, something like that. We could check this, but it's less important. Just know that the salt is actually stored in the hashed password itself. And so whenever, and again, any user could come here and see this, and that's not a big deal. It's actually okay that anyone can see what the salt is, because that's not important. The purpose is not to be some like mysterious thing. The purpose is just to mitigate the batch advantage of trying to brute force all of the passwords at once. Because hackers might be able to crack one password at a time, if we didn't use a salt at all, then if they cracked one and there are multiple passwords that were the same, then that would crack all of them at the same time. But by adding a salt, it makes this process slow and arduous, eliminating most of the advantages of pre-computing all of these hashes. Nowadays, though, computation is so fast and so cheap that even as far back as like 10 years ago, for about $1,000, you could rent cloud computation fast enough to attempt 700 million passwords a second. So you could just brute force all of these different passwords. And again, today that computation is almost certainly much cheaper and almost certainly much faster. So then we have to consider, how do we protect against a brute force attack of just randomly entering in as many passwords as humanly possible until you get a hit. And that's actually the problem that primarily Bcrypt solved. And if you want to get into the technical details, it implements this variant of the blowfish encryption algorithm's keying schedule and introduces this work factor, which slows down or determines how expensive the hash function is. So instead of being almost instantaneous, the hashing function can take up to like half a second or longer, which makes brute force attacks go from 700 million a second to like a lot less, orders of magnitude slower, which mitigates brute force attacks pretty significantly. So there's all these crazy things at play here that we have to consider when handling security and authentication in our application. But the primary one, the core of all of this, is to know that the bcrypt.hash is an essential way to store hashed passwords in the database. So let's actually go ahead and add our bcrypt work factor as a configuration variable in our environment. Let's go to config here and add const bcrypt work factor equals, let's go with 13. 13 is a big number. by 2 to the 13th is an enormous number, so that's going to slow things down pretty considerably, and it's very unlikely that modern computation, at least for the time of this video, is going to... 13 is sufficient, at least, at the moment. And so all we need to do is take that variable and import it into our model here. So we can say const bcrypt work factor. Bcrypt, how did I spell that? Something like that. Equals require ... config. Let's just make sure. Factor. Yeah. Okay, cool. I got it right. And then let's also import Bcrypt, since we're going to be using it here. Equals require Bcrypt. So now we can head down to the password here, and instead of leaving this out, we'll do this. We'll say const hashed password equals await bcrypt dot hash the credentials dot password, and then we will use the bcrypt work factor here. Now I'm using the await syntax here instead of the promise-based syntax we did here, but they're essentially the same thing. Instead, I'm just using a callback here, but it doesn't really matter. So once we've taken the hash password, we can then insert that into the database instead of the plain text password. So now, if we create a new user, we should be able to see their hashed password stored in the database instead of the plain text password. So let's try that out. Let's start our server. npm start. Okay, everything seems to be working. Let's head back to Insomnia. Let's say someone at u.them. Let's make the RSVP status one guest, and let's keep the same password, and let's send this. Cool. Now notice that took a little bit longer because we're hashing passwords. That's a good thing. It's not insignificant, but it's just enough to make sure that things worked. And we notice that things seem to look good here. Let's head into pSQL and make sure they are. We'll come here, we'll say pSQL. We'll connect to our wedding registration DB, and then we will select all from users. Amazing. Now look at that. The password is saved sufficiently here, hashed, and ready to go. Now it's probably a good idea to delete the user with a plain text password, so let's go ahead and do that. We'll delete from users where ID equals 3. And then let's select all from users again, and looking good. So now the question is, how do we allow users to log in once they've already signed up? So that's next, and probably last, but for now let's go ahead and do our get dance as well. Get status. I'm not going to add the security to this. I'm just going to add config and models. Oops, git add config models user, and then let's commit them with integrated bcrypt, and we're good to go.